Howdy and welcome back. So we're going to go ahead and I guess just briefly discuss some of the implications of choosing one graph representation over another within our program. So as we pointed out before we got into it about, say, the adjacency list implementation versus the adjacency matrix implementation, we said we have to consider kind of the storage space implications of maybe choosing one sort of representation over another for the type of graph that we'd like to accommodate within our applications. Likewise, there's always this kind of issue of time efficiency, and there's various, as we'll see moving forward, graph processing tasks that we might like to introduce or invoke. And the question becomes, well, what is the implication of using one representation in terms of the time to complete some operation, perhaps? How does it scale as the graph grows bigger? We said that the well, I guess we haven't said yet, maybe you've noticed, but at this point, we'll go ahead and point it out. The adjacency matrix representation fails on the first kind of consideration that we wanted to make. We said that in a sparse graph, we already acknowledged this part. In a sparse graph, we'd be wasting a lot of space because there'd be a lot of zeros there encoding non-connections. So we'd have this huge two-dimensional array that was allocated to represent the edges contained within some graph G. However, there's not a lot of edges, so that array is mostly zeros. Maybe, if you kind of look at the adjacency list representation, that seems like a more favorable approach to this. Likewise, graphs with millions of vertices are common in the space costs, so V times V, so maybe 4 million times 4 million, almost makes this implementation intractable. And again, by this implementation, I'm talking about the adjacency matrix representation. That's a huge block of contiguous memory that you're requesting from either from the runtime system, and it might not be able to be satisfied because, again, it's big chunk of contiguous memory. Whereas if we have these little nodes scattered all throughout memory, we're more easily able to find a little gap to put a small node opposed to, a row of a million contiguously allocated integer objects. So the adjacency list representation is going to more or less satisfy both of the considerations in terms of storage space and time efficiency for typical applications. And as such, we're going to go ahead and use this implementation throughout our course today. To go ahead and just conclude today's lesson, I just want to put up some complexities kind of associated with the two different representations that we've talked about today. So let's first consider the adjacency list representation. So the amount of space that we're going to need is essentially an array of V elements to store those pointers into linked list, and the number of, say, nodes on that linked list are going to be the number of edges within our graph. So the space complexity here, V plus E. If we want to add some edge VW into a graph using an adjacency list representation, this is going to be constant time. All we have to do is jump to, say, V's adjacency list and tag on maybe to the front of that list, so a constant time operation, W, and then jump to W's adjacency list and tack on to the front of it, V. At that point, we've absorbed the edge VW, the undirected edge VW, into our graph G. Now, if we want to check whether W is adjacent to V, that is going to require us to essentially iterate through, in the worst case, every node V incident to W. We won't know whether or not a connection between W and V exists until we've either found it in let's call it W's adjacency list, or we've hit the null pointer and looked at every node that is incident to W. So maybe I got that reversed. So same holds for V. So if you want to know if W's in V, well, it's going to be dependent on the degree of V, because in the worst case, you're going to have to traverse each of the nodes in the adjacency list to see whether or not one of them matches W. Hopefully that makes sense and I didn't confuse you. Just remember, anytime you're dealing with a linked list, you have to walk from node to node to node. And in this case, to know whether or not W is incident to V, well, you have to see whether or not there's a entry in V's list for W. And the same is going to go through if we want to iterate through the vertices adjacent to V, whether it's printing them or some other operation, we're going to have to walk through that linked list as well. So in that case, it would be the amount of time that would take would be dependent on the number of the degree of vertex V. Let's go ahead and contrast this with our adjacency matrix, the space. We have to store this connectivity in a V by V matrix. So the space requirement is going to be V squared. If we want to add an edge, this is constant time because all we have to do is essentially access, let's just call it M of V of W. So direct access to that particular location within our adjacency matrix. And we can simply add a 1 or assign a 1 to that particular slot, and then do the same for M of W V, provided this is undirected. But again, the constant time, this is constant time here. It's arrays afford us direct access to elements. We can jump directly to the slot allocated for telling us whether or not an edge exists between V and W, and just assign a value there to indicate, hey, in this case, there does. If we want to check whether W is adjacent to V, that is, an edge exists between the two, all we have to do is check M of V of W and see if we observe some sort of non-zero value. If we do, at that point, we know that, hey, an edge exists between the two. So W in that case would be adjacent to V. And again, this is just jumping directly to that location in the two-dimensional array. Whereas in the adjacency list, we jumped to the list and then we had to start the walking process. So adjacency list would not afford direct access to make this check, while the adjacency matrix does. If we wanted to iterate through all of the vertexes adjacent to V, well, we don't have this nice kind of list representation that only stores the nodes that are adjacent to V. Instead, we'd have to pull out the whole row M of V and then look at all of the values within that row. And if we observe, say, a non-zero value of 1, we would know that, hey, that particular vertex W is adjacent to V. However, if we were to observe a 0 there, we would know that, okay, that particular vertex W is not adjacent to V. So just to, I don't know, kind of wrap this home, if we wanted to know what nodes are incident to, what vertices are incident to or adjacent to vertex 1, we have to look at this whole row right here. We have to visit each of the elements 0 through 5 to know whether or not the vertices 0 to 5 are adjacent to node or vertex 1. For the list, all we have to do is jump into the list and begin walking. And in this case, notice we only traverse the actual edges that exist, and we're not traversing both the existent edges and those that don't. So this representation is storing, again, both the edges in existence and the ones that aren't, shown by 1 and 0 respectively. This list representation is only storing an entry in a particular vertices adjacency list should there be an edge between that respective vertex and a particular one under consideration. So I hope that's, I don't know, kind of clear. If not, spend a little bit of time on this. The two representations are, they're interesting and there's some interesting implications associated with them. But understand, moving forward from today, we're going to be tinkering with this one. Alrighty, that's it for today's lesson. I hope you learned something, and I'll see you all tomorrow.